In this chapter, we discuss about several methods, several estimation methods that use statistical information of some variables, some quantities, some especially the noise in the model. In the first video clip, we mentioned about the concept of mean square estimation that use the fact that the best estimator in the mean square sense is the conditional mean. That's the first important result. Okay, you want to estimate x given y. X and y are random variable with a joint distribution. So it means that you have information about the joint distribution between x and y. And the best way to estimate x is basically compute the conditional mean. That's the main result. And when we apply that result on a particular distribution, which is Gaussian, that conditional mean, of course, it has an explicit form and it is linear in X. That's information from the previous video clip. Today, we focus on the same concept. We still look for an estimator that is best in the mean square sense, which means that that estimator, when you compute the error, compute the square and then its means, that should be given the minimum mean square error. But in this video clip, we focus on the linear class of estimator. Again, the problem setting is still the same. We have the two random variable x and y. These guys are jointly distributed. Okay. But then when we say you want to come up with a linear estimator, you want to estimate x, okay? Which means when your estimator is linear, it means that that function of y should be parameterized linearly in y. Okay, so we have MMSE. We have we have all kinds of estimators. Is in a nonlinear class. This is a set of all kind of estimator h of y. H can be any nonlinear function. And then we're going to restrict to the linear case. Okay, in this one, so you assume the form of h, which is k times y tilde plus e of x, where y tilde is basically the y with the mean removed. Okay. We can just change the variable a little bit. We can define x tilde as x minus its mean. Okay, and then we follow the same concept. All right. Now we restrict h to be the linear form, like this. The reason why we have the bias term as EX, because you know that when you take the expectation of your estimator, that should be K times EY tilde plus E of X, right? And because Y tilde is it has zero mean. Okay, so that's why the bias term here is intended for HY to be unbiased, right? Because we want the expectation of our estimator to be the same as the value we want to estimate. Okay, so this is so the term here is to guarantee that your estimator is unbiased. Now we just plug it in. We aim to design h of y to have the minimum MSE. So the only thing that we can just choose, manipulate is the gain k. It's a constant. K is a matrix. Okay. The size of k, it's just the dimension that makes the dimension of x and y to be compatible. So x minus hy is going to be x minus k tilde minus e of x, all right? And then that is x tilde minus k y tilde, All right. So you want to choose k so that this term is minimized. All right. We can show that the linear MMSE estimator, the choice of k that minimize this is, I mean, it turns out to be the form that we all have seen before, which is h of y, the gain k is given by the cross correlation metric between x and y and the correlation of y inverse. Okay, my times this is the deviation of y from its mean and plus e of x. Okay, so basically this is a result that the main important we need to the main important result we need to show is that the gain k is given by this yellow matrix. All right. From this result, we want to comment that it turns out that the linear MMSE estimator just requires just the covariances of x and y. All right. This is not. This is a milder condition than the MMSE estimator. That you need the conditional mean of x given y. Usually, you need the joint distribution between x and y in order to compute the conditional mean. But if you restrict to the linear case, all right, the linear case, you don't need the whole distribution between x and y. All you need is just the second moment. Okay, this quantity. This form also, if you take a look, is also identical to the optimal mean square estimate of the Gaussian variable. So this is the same as expression we had earlier. Okay. All right. Now, we just need to show that, okay, the matrix K is given by this matrix. All right. The way you compute the matrix K can be done by using the what's so-called the Wiener-Hopf equation. Okay, so I just so I'm about to show that the optimal condition for the linear MMSE estimator is the matrix K that satisfies this equation, and this equation is called Wiener-Hopf equation. You will see that from here you would when you solve this linear equation, this is matrix K on this slide. Okay. Now we're gonna show how do we end up with this Wiener-Hopf equation. So first, we take a step back to take a look at the MSE. All right, we want to minimize this quantity. So we're gonna expand the 2 norm squared, but then by using the fact that the norm square is what is also given by this guy transpose, right, is the error transpose error. And then we also would like to take a note that because this is a scalar, so it also equal to its trace. And then we can use the circular property of the trace, which is this. All right. This is a circular property of the trace. And now we're gonna expand everything in this term. Expand the quadratic, the outer product. Okay. And so when we expand, okay, this is given by this equation. Now let's expand a little bit. Okay, Siddhipark, can you give the first term when you multiply this and this?
Yeah. X tilde transpose.
Okay, the next term.
Term is x minus k x tilde y tilde transpose.
Which one is first? Minus, can you say it again?
X tilde y tilde transpose k transpose.
Okay. Total Toto, can you give us the second term, the next term?
Minus
Mm-hmm.
minus k times y tilde x tilde transpose plus k times y tilde times y transpose k transpose.
Okay, all right. That's just how you expand the outer product. But then, okay, now you need to apply the operator trace and the expectation. These two guys, you remember when you take expectation and the trace is what? Is the sum of the diagonal, right? But these guy in the matrix, these are random variable, right? So can you see that the question is, can you swap the row of expectation and the trace? Are they the same?
Yes.
Yes, right? Because when you take the expectation of random things, random matrix, you just take the expectation element wise. So they are the same. Now, so if I apply the expectation first, I swap the row, you will see that, for example, expectation of x tilde, that is the covariance of x, right? X, y transpose, that's the cross covariance of x, y. Okay, and then and all the terms in here. All right. What are we doing here? We try to express the MSE as a function of k because we want to minimize MSE, right? Over k. So when we express, you will see that it turns out to be a quadratic function in k. All right, and now you're going to apply the optimal condition. You minimize MSE with respect to k, so you take the first derivative and with respect to k and set it to 0. And you see that that's how you are going to take a look at this function and see that this is a function of matrix. So when you take the first derivative, just use the result. For example, if a function is linear in x, trace of A transpose x, the derivative is A, all right? When you have a function that is quadratic in x, the derivative is A transpose x plus AX. If A is symmetric, all right, the first derivative is, in this case, is 2AX. Okay, so when you apply that result, the derivative with respect to k is given by this. You need to kind of express the term a little bit because the function involves k transpose in k. All right, please take care of the transpose thing. And then when you set it to 0, that is the optimality condition. Okay, then you're gonna have this equation, all right, when you just express it again, but that is the same as what given in the yellow box. All right, transpose the whole thing. That is the famous Wiener-Hopf equation. All right. The interpretation of Wiener-Hopf equation is that, okay, it can be also obtained from this condition. Expectation of x minus hy times y transpose equals 0. This is also equivalent to the form because your x minus hy is what? X minus ky tilde minus e of x, right? That is the same as x tilde minus ky tilde. Okay, and of course, expectation of these whole things equals 0 will give you the same condition as the Wiener-Hopf equation because it says e of x tilde y tilde transpose equals K is of y tilde transpose, right? And that is what? This is sigma xy, sigma yy. That's the same as Wiener-Hopf equation. But then we have seen this relationship before. The meaning is what? The meaning is x minus k y tilde is the residual, right? Is the residual after you estimate, right? It's after you estimate x using a function of y. And then y tilde, which is just a removed mean version of y, you can think of this as a function of y. We have seen this before because this is called orthogonality condition for Mmse estimator. Residual is uncorrelated with any function of y. Okay. So if your estimator is optimal, it must satisfy, the residual of such predictor, of such estimator should be uncorrelated with a function of y. So this is the justification of the Wiener-Hopf equation. The nice thing of the Wiener-Hopf equation is that it's just linear in K. You can solve it effectively. Okay. So to be conclude, the linear MMSE is given by this form. It is a linear function in y. The gain, the matrix gain that multiply with the deviation of y can be solved from the Wiener-Hopf equation. Next we have another related estimator. Okay, this is called minimum variance unbiased estimator, or Mvue. Okay. So by the meaning, we look for unbiased estimator that has the property that it gives the minimum variance or the minimum covariance. So let's take a look at the problem setting. Now the problem is still the same. You have variable x and y. These two guys are jointly distributed. What the only thing that is measurable is y, but you want to use the information of y to estimate x. You want to come up with estimator of the form h of y. All right. But now the way you choose hy, it has different goal. All right. The goal is that first you take a look at the error of the estimation. All right, you call it E. Of course, if you compute expectation of E transpose, that is the covariance of what? Covariance of your estimator. Okay, right? Because this is the error between x minus x hat. Okay. All right. Now, unlike MSE, that you compute the mean square error and you want to minimize it. Now you take a look at the error. Error is a vector, but you take a look at the covariance of this error. Of course, if you come up with different choices of your estimator h, that would give you different covariances. Let's say it's C1 and C2. All right. So if we want to compare, okay, which estimator is better, so we can compare its covariance matrices, and we're going to compare it in a matrix sense. And of course, what we know in the matrix sense is that C1 is bigger than C2 if C1 minus C2 is positive semi-definite. All right. And we know that when a covariance matrix C1 is bigger than C2, that is a stronger condition, because it's also implied that the trace of C1 is bigger than the trace of C2. Remember when you have when you have the covariance matrix, what happens when you take the trace of covariance matrix? Of course, that is trace of E transpose, all right? And then you can just swap the row, okay? And then the trace of E transpose E, and that is the same thing as the norm of E squared. So this is MSE, the mean square error. The mean square error is given by the trace of the covariance matrix. That's the relation. Okay, the covariance matrix is a matrix. Okay, please recall. What is the diagonal term of the covariance? Is the variance of all the components of the errors, right? The variance of E1, the variance of E2, the variance of En. So if you take the trace, you sum of all the variance of the error. Okay, and that is the MSE. Okay, so you would expect that, okay, if you find estimator that has a minimum covariance, but but if you have the minimum covariance, it seems that you would get the minimum MSE as well. All right, so now we're gonna see the result, how it turns out. Now we also, so the definition of Mvue is this is for any linear or any nonlinear estimator that is unbiased, and then achieve the minimum covariance by choosing a suitable edge. All right, but now in this video clip, we focus on the linear form of estimator. So again, we put the we parameterize the form with the F5 form. H is linear in Y plus some constant, and that constant will be chosen so that it has unbiased property. Okay, so now on this approach, again, let me emphasize that you're going to choose K so that the covariance matrix is minimum instead of the minimum MSE. Okay, with some algebra, you can just expand everything, expand the outer product, all right, and take the expectation and everything, and that is your covariance matrix. Okay, you will see that it depends on K and C, of course. First, we would like to, of course, minimize this guy, but in a matrix sense. But first, the first term you can choose easily is the term in C, because you need to make because now you can say you choose C such that this term is 0. This term is outer product, right? So it has to be non-negative definite. Then you have a choice in C. You just make this term 0 by choosing this one. Okay. It is also the same choice, so that this C, the choice of C that is given here is also the same one as to make HY unbiased. Okay, so if you just check this condition, it satisfies when C is given by this. All right, the next thing, okay, once you now you have determined C, now the only term left is to pick K, such that the covariance is minimum in the matrix sense. All right, so we arrange this term using some algebra. Again, you recognize that it is a quadratic function in K. Now you write it in a quadratic form, okay, and then please verify the term in the pink box. But then when you have expressed it like this, you see that it is again quadratic form, right? Quadratic form, so it's guaranteed that this guy is non-negative. It's always non-negative definite. Okay. Which means, does it make sense to be non-negative? Yes, of course. What you're deriving here is the covariance matrix, right? So with the property of the covariance, it has to be always non-negative. Any choice of K, you pick different K, you end up with different covariance matrix of the error. And now you just want to pick the one that gives the smallest covariance. Now let's rearrange the term a little bit. Okay, let's say K0 is a matrix that satisfies the Wiener-Hopf equation. Okay. Now the thing is, you can derive the covariance matrix f of k as a function of K0 and K. Add and subtract the terms. I'll let you verify it, okay, later. So when we, when we arrange the term in the yellow box, it gives us the meaning that if you want to pick K, that this guy is minimum in the matrix sense, what should we pick? Pink. Pink.
Yes.
Mm.
You mean that how can we pick it?
Yes, by looking at the expression of fk, k is a variable that you can choose, but you have expressed it as a function of k0. K0 is the gain that you can solve from Wiener-Hopf equation. So think of k0 as a constant, as something fixed and can be given.
Also, so K0 should be 0.
No, you don't pick K0. As I said, you pick K.
Pick K to be K0.
We should pick K to be K0 because
it will minimize fk. Because the second term will be 0.
Yes, because the second term will be 0 when K equal K0. So and also this is again this is the result that, okay, if you want to get minimum covariance estimator, oh, it turns out that you pick K to be K0, and K0 is solved from the Wiener-Hopf equation. And that is the same as linear MMSE estimator. It's nothing different, right? Okay, that's turned out to be important conclusion. Okay, that when you pick K to be K0 and you just plug it in, the minimum covariance is, okay, when you just substitute and arrange the term, you will see that the minimum covariance matrix is yet again this form. This form, we have seen it before several times, that it is a true complement of the 1-1 block, which is x covariance of x in sigma. This is exactly the conditional covariance matrix for Gaussian variable. Okay, so in conclusion, the linear Mvue estimator is given by, of course, linear function in y, and the matrix gain here is solved from the Wiener-Hopf equation. That is the same as linear MMSE estimator. Okay, that's a conclusion. In order to compute the estimate, you only need the second moment of x and y. Okay, nothing more. No distribution of x and y is assumed. Okay, and that's that's all for this topic. Let me mention that the result we receive here, this is a linear case. All right. If you consider a more general, like a nonlinear one, you need to. It would be hard to say in general because the way you expand the covariance, I mean, it requires some parameterization of h of y. Okay.